I'm going in. Good morning. 33464. I'm gonna have to remove you unless you change the name. Three, 464. Please identify yourself, or I have to remove you.
Oh, sorry. It just automatically did that.
Oh, no worries. So go ahead and try to change that. Thank you.
Good morning, Mr. Rosenthal.
Good morning.
Good morning.
Good morning, Mr. Rosenthal.
Good morning. Okay.
I changed my name.
Okay, good. Thank you. All right. I have a arithmetic sequence problem for you guys. Arithmetic sequence is a sequence of numbers in which you're adding the same amount or subtracting the same amount every time. I suppose I can make that slightly larger, maybe?
Mr. Rosenthal,
Yes, sir.
I decided to learn how to solve a Rubik's Cube.
I'm sorry?
I decided to learn how to solve a Rubik's Cube.
Oh, good. Excellent. Yeah, I've been playing around with my cubes a little bit yesterday.
I've been getting into like these drum pad things, and I just started, and it's really cool.
Mm-hmm.
Oh,
I actually finally figured out how to do it correctly. I got the first 2 layers solved.
Excellent. All right, folks, if you can address this problem, that would be great while you're in the next 5 minutes waiting around.
is this lesson 9-3?
It is. Yeah, just to remember the strategy on this is probably the best thing to do is have that lesson printed out. So you're not relying on my screen. My screen really should just be a guide to tell you where we are. But if you have it out in front of you, either printed or on another screen, if possible, you know, not everybody has that capability. But if you do, that's the best case scenario so that you're not relying on being able to see the screen because you'll have it in front of you.
Is this the beginning of 9-3?
Yeah, yes.
Okay.
All right, and anything you want to do to extend the problem out, you know, try to add to the problem yourself. What else did they not ask you to do that you could add to this to, you know, information that this is giving you?
What's the difference between term number and term?
The term number for this one is 1, 2, 3, 4, 5, 6, because that's the first term. So the term number is 1 because it's the first one. This is the second term in the sequence, so the term number is term 2.
Got it.
Then there's the term itself has a value. These are good things to think about. Okay, and oh, I'm low on power. I better plug in. We're about to start any second here now. Good morning, Tom.
Mr. Rosenthal, my school down.
I'm sorry?
My Schoology is down, so I can't get the lesson on my computer screen. Is that okay?
Schoology's been having errors.
Oh, yeah.
Just
At this
keep
point,
reloading.
at
Just
this
keep
point,
reloading.
you guys go ahead and mute. At this, Everett, no videos. No videos. Thank you. All right. So at this point, we're going to get started. So it doesn't matter. So just follow along. Ask questions if you can't see the screen. Okay.
Okay, thank you.
All right. So right now we're working on this warm up. It says here arithmetic sequence. It's a sequence of numbers that increase or decrease by the same amount from term to term. When this says graph the ordered pairs, you might be looking for something that you're not seeing. You're looking for this. You're looking for a set of these. No more video, please. Okay, so when you're looking for X, Y, and you're only seeing a series of numbers, you might be asking, well, where are the X's and the Y's? I'm not making sense of that. So they kind of give you a hint here. Term number, comma, see that? Term. So what do they mean by term number? Well, this is the first term. This is the second, the third, the fourth, the fifth, the sixth. All right, so you can actually put what term number you're talking about in a table like we did last meeting, where this would be the term number one, term number two, and so on. What is term number one? Term number one is 3, okay? So now you might have an idea for starting this problem. Go ahead and keep going. If you have any questions, let me know.
So, Mr. Rosenthal, you can always graph. Oh, you can always graph functions because this is a function.
Well, it doesn't have to be a function. Like a circle is not a function.
Well,
we
yeah.
talked about. And you can graph it.
Mm-hmm.
I'm not sure if that was answering your question, though. What is your question?
Like, I don't know if there's a certain equation for this. I mean, like we know the slope. Like,
Okay, so that speaks to what as you guys were gathering early, I was saying, once you're doing this problem, see what else you can add to it. What you're talking about is an add-on that I'm going to ask everybody to do anyway, which is to find an equation for this.
Okay.
What is the linear function that would give you the 97th term down the line?
Mm-hmm.
Okay, question in the chat was, what do we add to each? Well, look, how do you get from 3 to 10, from 10 to 17, 17 to 24? What are you adding each time? You can see.
It's not finished. It's in progress.
All right, I can hear somebody in the background. You have to mute unless you're asking a question.
I don't even have anything saying show.
What are the order of the quadrants? Like, could you?
Yes, that. So it's counterclockwise. We start with positive, positive, quadrant 1. Then negative, positive, quadrant 2. Negative, negative, quadrant 3. positive, then negative, quadrant 4. And we go in this counterclockwise rotation.
Mr. Rosenthal, is it okay if you check my equation that I put into the chat?
You got it. You're right on target.
Yeah.
Now you can go ahead and throw in, if you want to find out the 1000th term or the 100th term or the 99th term, you can just plug it in and get that answer.
Yeah. Okay.
Yes. So you're already where we need you to be by the end of it. That's wonderful.
Oh yeah.
Yeah. Did you answer these other questions? Did you answer C, I'm wondering?
Is mine right?
Yes, Oliver. Wow. You guys you're showing me a lot of understanding already. That's really good. All right, as you're working on this, let's address A. Okay, so I see 1, 2, 3, 4, 5, 6 terms. So that would be the X is going to be the term number. 1, 2, 3, 4, 5, 6. And then you can just see what each term, the first term is 3. And then it appears we're adding 7 each time. So 10, 17, 24, 31, 38. Okay, so you can see what you're adding each time. Do the points seem to lie on a line when you graph them? You guys got to mute or talk, not talk directly into the mic, maybe. Y plus 7, that's interesting. Oh, I like what Jasper's doing. He already found the 100th term. Great. It's not going to be 7x plus 3, but that is a great answer. I can see you're thinking, oh, you're starting at 3. That must be the y-intercept. But look at it. What do we know about the y-intercept? What has to be the x-coordinate at the y-intercept?
0.
What does it have to be again?
0.
Ah, it's got to be 0. So the x has to be 0. The first term is not 0, right? The first term is the first term. It's term number 1. So if you're trying to find the equation, you need to go backwards 1 and find out what happens when x is 0. And you can see the pattern. Count down. What are you subtracting each time? Is the same thing when you're going this way that you're adding each time. So you can get that starting number, Angus, when you go back. Okay, and then your equation will be correct. Let's see if you already got it. Yeah, you got it. You got it now. Okay, so graphing this. Now this is going to be interesting. My graph is not going to, it's going to be skewed because I'm going to count by 1s on the x-axis, but on the y-axis, I'm not going to count by 1s. All right? So what is that going to do? It's going to flatten out what my graph should look like. Okay, there's 1 through 6. Okay, what might I count by here? What might I count by?
2.
You think I can fit that in there?
5.
Mr. Rosenthal,
Yes.
for C, I found the values for those 3, for those 3 points, the y values for those 3 x values in C. But when it says an arithmetic sequence have these values for x, does it mean when you list it?
Can an arithmetic sequence have these values?
Oh, in between the whole numbers?
Yes.
Oh, okay.
Okay, so try to answer that question as we're talking about graphing this. Okay, so I made these marks and I have 8 of them. So I think if I count by 5. Again, if you're lost at any point, please speak up or send me a question in the chat. Okay, so 1, 3 is about there. I'm kind of estimating it. There's 1, 3. 2, 10, right there. 3, 17. 4, 24. 5, 31. 6, 38. And the question is, do the points appear or seem to lie on a line? And you can answer that out loud. Do they appear to lie, or in the chat? Yeah.
They're on a
Jasper,
line.
mute your mic. Your mic is going crazy.
Yes. So who is that? The mic is not working properly?
Jasper, you should mute.
Okay. Thank you.
Wait, who? Me or the other Jasper?
I think we're good now.
It's a line and it's also a function.
So let me ask you, should I then connect them and make a line? And that will kind of speak to some of the other questions we're going to ask you about this. Okay? But, okay, so people are saying in the chat, yes, they seem to lie on a line. Why would we think from this data that they would lie on a line? Anybody? Let's say we didn't even graph it.
Because none of the x-axes are the same.
Because it all goes up the same way.
Okay. So can you expand on that? What do you mean it all goes up the same way?
It follows a linear rule.
Which means what? What does that mean?
Slope. I was talking.
Okay, go ahead and continue to talk.
It adds each time by 7, so we know it's a line. It doesn't twist or turn. It always goes up by that number.
All right, but what if I didn't go up by the same amount here? Would it still go up by 7? What if I jump from 2 to 4 instead of stopping at 3? Would it go up by 7 if I jump from 2 to 4?
No, on the y-axis it would go up by 14.
So are you saying that the amount that it goes up here depends on the amount that it goes up over here?
Yes.
Where have we heard that before, where one value increases depending on how another value increases or decreases?
Functions.
Functions, okay. What else? Where else has that idea? Anybody else?
Linear equation.
The idea.
Multiplication.
Fine. Okay. Any other terms?
Linear.
Y equals mx plus b.
Okay. What part of the mx plus b is speaking to the fact that as one value changes, it depends on how another value changes? Which one of the y, mx, and b is that referring to?
The
M.
What is m?
Law of proportional equality.
oh, the intercept.
Slope.
M is slope.
Slope is what? Change in y.
As x increases by 1, y must increase by 7.
And
The change in x.
And what is x? X is which type of variable?
Independent.
It's independent. And y
Totally.
depends on x, right? So y changes as x changes, okay? And that's our slope. Okay, so you could see that a slope exists here because as these are changing by 7, it's based on these increasing by 1 each time, all the way down. And these are just the different term numbers. So of course it was going to be the first term, the second term, the third term. So that was kind of set in stone already with the sequence. But the results could change. I could give you a whole nother problem with a different sequence. And these would just be different, but these would be the same. Great. All right, so I think we've answered A. Let's go to B. In which quadrants would this graph make sense? I think that's a quick answer. We already said does everybody remember what quadrant this is?
Again,
This
now.
is one. Well, then why that question? That seems like such a simple question. Why not other quadrants? What would it mean for a point to be over here?
That it would have to be
Negative.
Negative, and then
What would have to be negative?
x would be
The
negative.
x would have to be negative.
Okay, x would have to be negative. So over here, x is negative, y is positive.
Yes.
Yeah.
X is the term number. So you'd have to have a negative term number, right? You can imagine a negative term number because it would just be, right? Right? If you continued this line down, you can imagine it passing through the negative. But in the context of our sequence, you don't have term number -1. Doesn't exist here. All that exists is term number 1, right? And then on. Then you have term 2, 3, 4, 5. So these points over here and any point over here Doesn't make a lot of sense. What about points being over here in the positive, but down here? What's wrong with a point being in quadrant 4?
The line can't,
How do you even?
can't go there.
Axis is
Why can't the line go there?
Because if all of your x-axes are positive, then none of them with the y will be negative.
Is there a sequence where the first term is here, but then the dots go down? Can I have 3, 0, -3, -6, -9, -12? That's a sequence where it's going down by 3 every time, right? Then
But it doesn't go into the quadrant 4.
well, what if my y values kept dropping until I got into the negative? What if my slope was negative? My y.
If you started with a positive, well then it's.
Hold on 1 second. Let me say this again. If I were to use a different sequence where these numbers were falling, they could fall down into quadrant 4. Is that the case in this particular sequence?
No.
No. So
No.
you're not going to see any dots in quadrant 4. Okay? And now let's move on to C.
But there's like one place where it could be near 0.
You right around here, you mean?
Yeah.
That's okay. So we'll have to examine that. Could it be? Where is your first term? No, so this is what question C is going to answer. If you connected all the points, you would be including all the x's in between. So here is an x of 1 corresponds with a y value of 3. Here, an x of 2 corresponds with a y value of 10. But what would 1.5 mean? Where would this be? It would be somewhere here. Okay? But there is no outcome.
The line includes all of the values for all the.
Right, how would I cover all the infinite points in between?
Doesn't this line actually go into quadrant 4?
Wait, but hold on, hold that question for a second. If you were to cover all of these different x values, can this arithmetic sequence have these values in it? Well, when I make a line, it appears the answer is yes. But then go back up to the sequence.
It would be a decimal sequence. It would have to be a.
The sequence only has these numbers. This is basically the range. The range is what these outcomes can be.
Yeah.
Can the outcome be anything other than a natural number here? Or a whole number? If you're adding 7 every time, are you ever going to get anything that's not a whole number?
You're only going to
Only
get
whole
a
numbers.
whole number. You're not going to have a decimal.
Not only that, you're not even going to get any whole numbers in between. You're only going to get these
Decimal.
points, only those specific points that are up by 7 every time. So here's 7. If this is 7, and I go up another 7 from 38, I'm going to be up here at 45, right?
If decimals were included, you would have to find a whole new pattern. It would have to be
With another sequence, right? But given this sequence, so this is a field of mathematics called discrete mathematics. Discrete mathematics is not necessarily talking about this continuous line as a line like we've been doing in class. All we care about in this sequence are only these points. Only these points exist. It does go on forever. Okay, so here's something I'm going to show you that I don't think I've ever told a pre-algebra class. There's 2 words that are used interchangeably incorrectly. What's the difference between continuous, okay, and continual?
There's no difference.
There is a difference.
Really?
And I'm gonna paint it for you right now. The green line is an example of a continuous set of points. There's no break in it. It includes all infinite points in between any 2. Continual is like the brown dots. It is a pattern that goes on forever, but there are gaps in between. that don't exist in our sequence. Nothing exists in between 2 points.
This
Only
is a
the points
continuous
exist.
sequence.
Okay, so that's called continual. These points continually go in a linear pattern.
So the difference is a line?
Continual. How about a heartbeat? A heartbeat is continual. Dot, 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 dot.
But blood flow is continuous.
Probably, yeah, I would hope so.
Most of the time.
Okay, but yeah, so continuous, no breaks in the line is continuous. Continual, if I keep a pattern, dot, 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 that's continual. But if I do this, that's continuous. Okay, there's no break in it. But if there's a break in it, but it still repeats, dot, 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 that's continual.
What if
Okay.
it's a ray?
You don't want to hear the
Even if it's a ray, it's either continuous or it's a continual ray in one direction. All right,
Okay.
so I don't want to go too far into that. So, answer to this question: can an arithmetic sequence have these values? The answer is no. You can't have term number 1.5, right? You can only have term number 1, term number 2, term number 3, term number 4. You don't have half of a term. All right, your terms are ordered, and they're from the set of natural numbers. Term number 1, 2, 3, not even from the set of whole numbers. You don't have term number 0. But when I ask you to make an equation for this, which some of you did, you do have to find out theoretically what would term 0 be.
What 1 point?
So what you did here is you subtract 7 each time. What happens when you get to term number 1 to find out what term number 0 is? You subtract 7. So you get term number 0, okay, term number 0 is the 3 minus 7. You get the -4. You have now found what? In an equation, you have found the y-intercept. You guys already found the slope, which was the change in y over the change in x. You said the y was increasing by 7. You also told me that depends on the x increasing by 1. So you told me the slope, which is m, is 7 divided by 1 is 7. You have the slope, you have the y-intercept. That's all you need to make your equation. You have the m and the b. So what's my equation? Y equals m
7x minus
x plus my y-intercept, which is negative, so I can say minus or plus negative. Okay? Or I can write it in function notation. My result, which in this case is what the term value is going to depend on what term number you plug in. So if I want to know what the 99th term is, let's go make something easy. Let's do the 100th term. All I have to do is 7 times 100. And remember that I started at -4, so I have to take away that 4. Okay, so 700 minus 4 is 696. That's the 100th term.
Mr. Rosenthal.
That's f of 100. F of 100 is 696. I input 100 and I get out 696. All right, questions? Yes.
Mr. Rosenthal. So I found an equation to find, like, say 100 in the term numbers. It would be 3 plus 7 times the term number. Is that correct?
All right, let's see if that works. 3 plus 7 is 10. 10 times the term number. Let's say the term number is 100. You would get 1,000. Is that what the term is? Is that what the term value is at the 100th term?
No.
Is it 1,000? It's 696, right?
Yeah.
Okay, so we're trying to understand it in terms of slope-intercept form. Understand how it's changing. Well, we see how it's changing every term. It's adding 7. That explains the slope. What happens at term number 0 is what the y-intercept is. It's where it starts on the y-axis. You don't have that here. Term number 1 is not what you're looking for. You're looking for one term before that. And you would follow that pattern back to get to that. -7, -7, -7. That leads us to the -4. Has to be our starting point. Starting at -4, add 7 each time. Well, what if I want to know what the first term is? I would put a 1 in there. 7 times 1 is 7, right? Adding 7, a positive 7 to -4 takes me to my first term. If I want to add 7 twice, that will take me to my second term. If I want to add 7 to the -4 3 times, that'll take me to my third term. And that's what this equation does for me. Any questions about that? All right, that was a good warm-up. Let's get into the lesson. Here we go. All right, what are we going to be studying today? I think we're well prepared now to talk about, and I will angle this up, constant rate of change. What on earth is constant rate of change? I think you already could figure out what that is. If you want to put that in the chat, what you think that is, go ahead, type that in the chat. Is there another word for constant rate of change that we've already discussed this morning? I'm going to look. Aha, it's already coming in. You got it. So that's our topic today. People are saying slope. You can see it here. Constant rate of change. Slope is going to be one of the most important things we discuss throughout algebra, calculus, and so on and so forth after. It's a very, very important topic. How things are changing. As a matter of fact, life itself depends on change, doesn't it? So if somebody says, why is this interesting? Why is this important? It helps define life itself, change, how things change from, if everything was the same, then that might even be the definition of nothing. I wonder, we'd have to think about that. So now we're getting very philosophical, but if you think about it, if everything was the same as everything else, and you couldn't distinguish between anything from anything else, would that be something or would that be nothing? Okay, so, so change, when the fact that something is different from some other thing, all right, if it all started in the same place and now it's not in the same place, okay, that change is, we're going to put that into math language here. The math is pure. It's going to describe that, all right, and you already are on the right track to understanding it. Okay, again, this is simple. We're studying lines right now. How does a line change? What does that mean that a line changes? It doesn't mean much. What it means is that any point on the line changes to get to another point on the line, from an A to a B. Okay? So we're changing, and what is a point? What did we say a point is?
Location.
It's a location. So if you change your location, we refer to that in physics as
Moving.
Displacement. Or we could call that a dimension or a distance or a length, a width, a height of something. Okay? All right? What happens if I change my displacement? What happens if I change this? What if instead of from A to B, I change the distance from A to C? Then I've moved, haven't I?
Displacement.
Changing displacement. What if we change that with respect to how, remember, we're changing it based on something else changing. This displacement changed, but in order for it to change, something else had to change. Let's call that maybe time. So if we change our distance, the change in displacement, over the change in time, what are we talking about in physics?
Distance.
Well, displacement is like a distance, right?
Yeah.
Well, if I change my
Displacement
distance over time,
Movement.
movement, how do we measure movement?
Reference
Points on a number line.
Okay, keep going, keep going.
Reference point.
What if I'm moving somewhere over time? What if I go really far in a short amount of time? Or
Speed.
okay, so speed is magnitude, but if I actually put it in a certain direction, we're going to call that
Velocity.
Vector.
Velocity.
Oh yeah.
Velocity.
Okay, and this keeps going on, but let's do it one
Yeah,
more
it was
time.
right.
What if I change my velocity over time?
Acceleration.
Ah, you got it, acceleration. So
Nice.
in calculus, you're going to be doing something called the derivative, where what does this look like? What if I change we can always change variables, right?
Yep.
What if I change that to a y and that to an x? Change in y over change in x.
It would be the slope.
Oh, it's a slope. So the derivative in calculus is going to be a slope. It has to be. Look at it.
Oh.
All right. So the derivative of displacement with respect to time, as time goes by, is velocity. And you're talking about a slope.
Yes.
It's a slope. So we're learning slopes for lines, but it's going to apply later in calculus. You're going to need this information.
Because it's like over like an hour. It was like over an hour. It's like 30 miles. Like if you change the time, then
Yes, right. There's dependence there. There's dependence. The displacement is going to depend on the amount of time taken. And if no time is taken, the displacement probably doesn't change. Okay? All right, and then acceleration, something to think about is if I jump out of a plane or you're on a roller coaster, and you feel your stomach drop, right? In the beginning, when you first start to drop, you are moving a certain velocity. But that velocity is slow. At the very, very split second that you jump, you're actually not going that fast. As a matter of fact, I know that I would be okay if I just jump in the air and land. I did not give my body enough time to start picking up speed. So the velocity I started to fall at when I jumped is not very fast, because if it was, I would have just hurt myself, and I didn't. All right? But if I were to jump from further up, it might hurt a little bit more, and further I go. Why? Why would it hurt? Just because the distance is different? Not because the distance is different. It's because my speed, my velocity gets faster. And the faster I go when I hit the ground causes more pain, doesn't it? Or damage.
You're accelerating.
Right. So what must be changing is my velocity changes due to what force?
Acceleration.
What's causing the acceleration?
Gravity.
Gravity. You got it. Okay. So that's where this is all going. So we really, really have to understand rate of change.
Wait, Mr. Rosenthal?
Yeah.
What's change in acceleration over change in time?
It's called jerk. So if I just pull somebody like that, okay, then the acceleration is not constant because my muscles are not pulling the same throughout the pull. All right, so I'm not accelerating the person at a constant rate of acceleration like gravity. Yeah.
Isn't that how? Wouldn't that hurt someone? Because say if you tied a rope around someone's waist and you like had a hydraulic piston and you release the piston and it jerks them forward, wouldn't they get really hurt because their chest was traveling faster than the rest of their body?
It depends on the force. Okay, but we're gonna move on. So I think I got you guys hooked. So let's get into it. The math stuff. Let's get into the math.
Ooh.
Okay, math.
All right, so let's define our terms. A rate of change is a rate that describes how one quantity changes in relation to another quantity. It's like time. When time changes, maybe the displacement from a certain point changes. In a linear relationship, the rate of change between any two quantities is the same or constant, like going up by 7 every time. That doesn't change in a linear pattern. What would happen if it did change? What if it's going up by every time I move to the right one, I go up 3. And I go to the right one, and this time I don't go up by 3, I go up by only 1. What happens when, remember what we said last meeting, through any 2 points, there is exactly what?
One line.
There's one line that goes through these points. What happens if I break my pattern and I stop here? Then you break the line, and you get a new line. Okay? Which is fine, but this is not representative of a single linear pattern. This is 2 separate patterns. Okay, so in order to stay in a line, you can't break the pattern of change. That's why it's going to be constant rate of change, because it has to stay the same along a line, or else it's not a line anymore.
What if they all
Broken
went
line.
through the same line? Can
What?
they all go through the same line?
Could these 3 points belong on the same line?
Oh, not a like.
Are you asking if these 3 points could be on the same line?
They wouldn't be on the same line.
They would not be on the same line. Only if the rate of change to get from this point to the next point stays the same.
If they were like if they were all part of the same all part of the same, like if it was all part of the same function, could it technically be up if it was going like the
Well, it's not.
like it went like if it went to the right, it went to the right 3 and then up 3 and then to the right 3 and then up 4 and then it just kept increasing like that, would it be a parabola?
Ah, that's interesting. Okay, so a parabola is exponential, all right, which is what we're using.
That's just staircases.
Which is what we're using to explain the spread of the virus, right? So you're getting something that looks like this. Starting in one position, let's displace, right? Let's go to another position. As we move over, we're going to move up 1 to 1, okay? But let's say that I move over 1 again, and this time I move up 3. And then I move over again, and I move up 5, right? What's happening is, if that was in a straight line, it would look like that. If it was in a straight line, what's happening to the slope of each time? The slope is increasing each time, right? So you get this curve. Okay, so it's no longer going to be a straight line, it's going to be a curve.
Yes.
Right? So that is not a linear pattern. We are going to stop here at linear patterns today.
Y
This
equals
is
a linear pattern.
if we finish the curriculum early, I'm going to get you guys into some of this quadratic pattern.
And so, Mr. Rosenthal, the stuff that we would be learning is the stuff that like I've been doing with like the parabola and.
It's open. When we finish the book, it's sky's the limit. We can do whatever we want.
Yay.
We learned quantum theory. I've been wanting to learn it for quite a while now.
That we're not going to do because I'm not an expert at that. All right, buddy, I'm going to give you about 60 seconds to look at this and figure this out for yourself. Go.
About the orbits.
Go ahead and mute for right now. If you have anything you want to type to me, go ahead and do that. And just have another 45 seconds to do this problem.
What's
I
the
had my answer in the answer
distance?
key. I mean in the chat.
How is the distance measured?
In feet. Ten seconds. While you're doing that, I'm going to check attendance here. See, we just can't quite break that 60 number. We have 56 participants. I really want to get over the 60 mark. I'd love to get everybody in here.
Isn't 57 like way more than there used to be?
Who is... I just saw a name that does not belong. Guys, don't change your names to something else, please. Who is TTREVEAY?
I just wrote my name in Pig Latin. That's me.
Who's Tom? What is his name, Tom? I know that.
I have a guess.
Everett.
Oh, Everett. Everett, please keep your name. Keep your name. Okay, here we go. Time is, we're 2 minutes now.
Tom
We
the
doubled the time. Okay, so what did you guys come up with for, what did it ask for? The constant rate of change. What did you come up with?
6.
I see people typing in this, and I see people typing in this. Which one is correct?
It's the. Do you want us to type it into the chat, or can we say it like?
Somebody said both.
Well,
Does it say which one depends on the other one?
I mean, a slope
No.
is delta y over delta x, not
Well,
delta
what is
x.
delta y? Let's not even have a variable. What is y? What type of variable is y?
The dependent.
So
variable.
change in the dependent variable
Depends on
over the
change
change in the independent.
variable.
Right? So then nothing here tells you which one depends on the other. So because it doesn't do that, you can make an argument for, well, the time it takes to do something, which is travel on a zip line, the time it takes is going to depend on the distance you want to travel. I can make that argument.
Yeah.
I can also say the distance I travel depends on how much time I travel for. Okay? Let me tell you, so both, it's true that both could be correct. So what we need to do is define our terms here. All right? Typically, we like to, what you're going to see, so both are correct. It's not wrong to do one way or the other, but I just want to tell you what you're likely to see in physics problems, in future math. You're going to see that that time is usually here.
Yeah, it's more
Time is
reasonable.
usually there. Things are changing as time changes. Okay? And another thing is, in a table, typically it's X and then Y when it's in a horizontal format. I'm just telling you that's typically what we do. When I test you, it'll be the same, where it's X on the top, Y on the bottom, going horizontally like that. Okay? So it's counterintuitive. It's not obvious that you're supposed to put the bottom on the top and the top on the bottom. Okay? All right? So I would say that the distance here depends on the time. Okay? But if you did it the other way, that's fine. And what you want to do is you don't necessarily want to put 12 over 2 or 24 over 4 or 36 over 6. But what if I did? So let me back up. Delta distance, change in distance is what? Every time it's going up by what?
12.
12. And the time is going up by how much?
6.
2.
Let's start.
No, 2. I'm sorry.
It's 2. The change in time is 2 seconds at a time. So it's going to change 12 feet every 2 seconds, which we will simplify to 6. So we can say the slope is 6. If you switched it and you did the reciprocal,
Amazing.
you would get 1/6. Now, what if I don't do change? What if I do any given distance with its input and output? What if I take any input and put it with its output and do output divided by input? What would I get in this problem? Do I get the same thing every time? 12 divided by 2.
Yeah.
24 divided by 4. 36 divided by 6.
Yes.
That means it's proportional.
Ah, yes! Score! That means it's proportional. That's what I was going to.
Yeah, there's no y-intercepts. I mean,
Yeah, if this matches your slope, it's proportional. It also means what? That this line, it's a line because it has a slope, but it's proportional because it did what?
It goes to the origin.
It goes through the origin. Let's make a connection right now to our warm-up. Follow this backwards to find your first term. -2, -2, -2, -2, -2 gets you what? 0. This one's -12, -12, -12, -12, -12, -12. Ah, so what was your coordinate here?
0,
0,
0.
0.
0, 0. It goes through the origin. Excellent. It's proportional.
Yay.
Why is it proportional? Because each of these ratios of output to input are equal. What's the definition of proportion?
And two things are equal, or
Two things, two ratios.
two ratios that are equal.
Okay, so if all of these ratios are equal, that's the definition of proportionality. All right, I don't know what to do with you guys. You guys are just too far ahead. That's wonderful.
Yeah.
Okay, any
Try to be as
questions?
smart as
Yay.
everyone else.
Any questions before we move on?
Okay, yeah, I have a big question.
Big question, go.
Okay, what does the delta signify?
The delta?
Yeah.
Change.
What do you mean by change?
Did 12 stay at 12 throughout the whole table?
No.
So what did it stay the same? If it didn't stay the same, then it must have done what?
Change.
Ah, changed. How much did it change by here, between the first two?
By 12.
At that rate of change, did that rate of change stay constant throughout?
Yes.
Okay, and what about time? Did time stay the same?
Yeah.
Time stayed 2 throughout the whole thing?
No. I mean, it changed by 2 through the whole thing.
So, and that was constant?
Yep.
Okay, so the change in your distance and your change in time remained 12 and 2, didn't it?
Yeah.
Throughout the table, yes?
Yes.
All right, so when you simplify that, that's what your slope is. It's the change in your dependent variable with respect to the change in your independent variable. Or the change in y over the change in x.
Couldn't you say just it's like what you multiply this top one, the dependent variable, to get the independent variable? Or the other way around, I guess.
What, I multiply this?
Well, what you would multiply the top to get the bottom.
Oh, it's what I multiply by the top to get the bottom.
Because that's also 6.
Can I multiply the top by 6 or the bottom by 6?
You multiply well, you would multiply the bottom. Oh, okay. Okay, I get it.
Now you're talking about how do I get from maybe an x value to how do I get from an input, which would be an x, to an output, which is a y? How would I get from one to the other? Then you might be using a scale factor to do that.
Oh.
So if I have an x, how do I get from this x to that y?
6.
Then if it's proportional, then there would be a scale factor that would link each input to each output. And that we usually use k for that. Okay, so each input can be multiplied by some k scale factor, which you found to be 6, and that would work only when when it's proportional. If it's not proportional, then all your output inputs are going to be different. They're not all going to be 6. All right, that was heavy. That was a lot of information. Let's move on. Okay, so you can use a graph to find a constant rate of change. So it looks like we're going to be doing some graphs. Okay, this is a tough concept.
Mr. Rosenthal?
Yes.
I have a quick question.
Go ahead.
So do we put delta x over delta y or delta y over delta x?
Well, look right here. Which one depends on what? How do we usually do it? Is it x depends on y or y depends on what x is? Does your output depend on the input or does your input depend on the output? Remember our function machine? You put something in.
The output depends on the input.
Okay. And output is y or x? Typically, with our equations. What's the output?
Y?
Yeah, so you got it. So the change in y over the change in x.
Okay.
X is independent. Y is dependent.
Okay.
Got it?
Yeah.
Okay, good. All right. So let's handle this next concept, which is difficult. I usually like my smartboard for this because I can take a circle and I can increase it and decrease it quickly for you.
We're doing
All
this.
right. All right, so I'm going to read this out loud and we'll try to make sense of this. A circular design on an internet advertisement has 2 circles, one that is decreasing in size and one that's increasing in size at the same time. find the constant rate of change for the radius of circle 1 in the graph shown, and then interpret its meaning. So let's go ahead and grab this graph here. So let's see, what are we doing? We're doing the constant rate of change for the radius of the circle. So let's take a look. Here's the graph of it. Let me shrink this down to 220 or 215.
I can barely.
There we go. It fits. Yeah.
Wait, is it counting by 1?
Yeah, I'll put that in for you. But here's what I want you to understand. You have one circle that starts out. So let me start with circle 1. Circle 1 is this line. What does it mean that this circle starts out here and the blue, dark blue one starts out down here? What does that mean?
It means that circle 1 was larger and then circle 2 was smaller.
And then what happened over, what is number of seconds? It's measuring what?
The time.
As time goes by, we are moving what way? To the right.
Yes.
What's happening to, what's this? Radius of the circle as time goes by of the smaller circle. Oh, by the way, what was the radius of the smaller circle at the beginning?
It was the origin 0, 0.
So it started with no circle there at all.
So it's proportion. It's proportional.
So when you first saw this screen, this advertisement, how many circles did you see?
1.
You only saw
one.
You only saw circle 1, right? And this has a radius of 5.5, by the way. That's 5.5.
5.5 what?
Centimeters.
5 centimeters.
Circle 1 radius was at 0 seconds, input 0. My radius was 5.5 centimeters. There's a starting coordinate. That's my y-intercept. At the circle 2 radius at the beginning, we call that initial radius. So I'll put a little 0 there. Initial radius, R0. My initial radius at time 0 was 0. By the way, which one of those circles will represent proportionality?
0, 0.
Circle 2. Circle 2.
Yeah, circle 2 will be proportional, but circle 1 will not, because it doesn't come out of the origin. All right, so, okay. So what happens over time is this circle's radius is growing, this circle's radius is shrinking. All right, when do they become the same size? When are the two circles congruent in the graph?
I can't read that.
It's so blurry on even
I'm not asking you for the exact point. Conceptually, where would that be in the graph?
What do the points mean? Like, do they intersect?
Around 4 or 5.
3.
I don't want the number because it's hard to see.
Circle 1 and
the
circle
lines
2 intersect. Where they intersect.
Yes. Okay. Good. So where the lines intersect, this is called a system of linear equations. System of linear equations or functions. Okay. That point where they intersect is called the solution to the system. Okay, that's for future reference. That location is where what's true about the circles at that point?
That they're the same size?
They're the same size. So those two circles are congruent at that time and at that radius, whatever that is. I'm looking right at it and I can't tell because it's not right in a corner. So it's at close to 5 centimeters. Just under 5, maybe 4.8 or 4.75 centimeters. That's when the circles will be the same size. What about after that?
Then 2 is bigger.
Yeah, and then circle 2 becomes bigger. Okay, so now I think I've painted the picture for you of what's happening with these two circles. Okay, so then what we can say is it's increasing at a constant rate and the other one's decreasing at a constant rate. It says here, find the constant rate of change for the radius of circle 1, then interpret its meaning. Well, I think that we already have its meaning. All right, so all we need to do is interpret it. So how would we know what this is? It started at 0, 5.5, and then let me go to any other point where I know where it is. How about this point? This point is at 5, 4. So I'm talking about circle number 1. So here's what I'm going to do. I'm going to get rid of this. Circle number 1, after 5 seconds, is at a 4 centimeter radius. What would the rate of change be? Try to figure that out. I'll give you 1 minute. Go. You can ask me any questions.
What's the rate of change?
What is the rate of change?
Yeah.
The delta y over the delta x. How is the circle's radius changing with respect to how much time, the change in time?
I was trying to trick you. You said we could ask any.
Oh.
There be a direction and a difference in the distance between them.
I'm sorry, say that again. You got to speak a little away from your mic, maybe?
Can there be a direction, like a negative or a positive?
Yes, good question. This circle is getting smaller. How can you tell the difference between a circle that's getting bigger and a circle that's getting smaller? We know directionally how to do that. It's with positives and negatives.
Monodirectional.
Can we type our answer into the chat?
Sure, that would be great.
I put my answer in decimal form because I realized that I can turn it into a decimal as easily as.
Did you have to round?
No.
No, good. So that will give everybody else hope.
Mr. Rosendahl?
Yes.
So you just graph this. What does it mean when it interpret the meaning?
Interpret the meaning. We talked a lot about the meaning of these graphs already. So find the constant rate of change for the radius of this. Oh, so interpret the meaning of the rate of change. What does it mean? Once you find out what the rate of change is, what does that rate of change mean?
It means a lot of things.
Well, let's find that first. Okay, let's go over it. So the radius changed. It went down here by how much? Say it out loud.
1.5.
It went down by 1.5. Remember, this is how the radius changed. Delta R. Delta R. And time is the other thing that's changing. How much did the time change to get the drop of 1.5?
It changed by 5.
It increased by 5, didn't it? And so to do this calculation, it's just a negative divided by a positive. So my slope here, or my rate of change, will be negative. And then I have to do this math. So how do I do this? 1.5 divided by 5.
Negative 0.3.
Yeah, he was about to do it.
And there it is. But what does that mean? Or as a fraction, what would this be? This is 3 what? What place value is that?
It's 3 tenths.
Negative 3/10. I like it like this, but that's fine too. What does this mean?
That means that's how us the.
Go ahead, Everett.
How
What
much does circle
mean?
radius change?
What is the negative 3 and what is the 10? Tell me what those mean.
The negative 3 is the quotient of negative 1.5 divided by 5.
Now what I mean, in the context of our circle shrinking problem.
They're the slope?
It's a circle shrinking.
Okay. The circle is shrinking by how much over how much time?
It shrinks by 3 centimeters every 10 seconds.
You got it. That's it. That is the way. That is exactly right. That is the meaning of that. The circle is shrinking 3 centimeters every 10 seconds. You betcha.
Yeah, I got it right.
Now, what about this one? The circle is shrinking 3/10 of a centimeter. This
Every
is
second.
Yeah, per second. You got it. Per 1 second. That's right. You got it. All right. Let's see what else we have. I'm just going to look ahead real quickly and see how much we have. Yeah, there's no rush. Yeah, no rush. Okay, guys, I'm going to dismiss you now, and we're going to continue where we left off tomorrow. All right, so I am open for office hours until you guys don't need me anymore. I'm going to just keep it open.
Okay.
So I'll see you all tomorrow. Great job, everybody. I don't have any additional homework to give you right now. We'll finish the lesson tomorrow, and then I'll give the homework. Okay?
Thank you.
You are dismissed. Thank you, everybody.
Bye,
And I'm
Mr.
open. I'm going to stay open.
Rosenthal.
Bye.
Bye.
Bye, guys.
Bye.
Okay, so I have a question about the zip line one.
Okay,
Bye.
let me go back to the zip line.
And the room just got a little bit smaller.
That's okay.
Like 30 people.
How many people are left? Oh.
All right. Zip line. Go ahead.
Okay, so it says find the constant rate of change between its quantities. Would that rate of change be 1/6?
That's if, okay, so you're doing one delta over another delta.
Yeah.
You're doing delta time, change in time over change in distance. Then it would be 1/6, yes.
Isn't it S over D?
Oh, those are just units. So this would be 1 second every 6 feet.
Are there any like catches that it's like something else you have to do, or is that just it?
But this is not how I would have expressed the answer, just so you know.
How would you have expressed it?
I would have switched these, the reciprocal. I like to do the change in distance with respect to the change in time. As a matter of fact, we talked about that. What in physics is that? When you change your distance or your displacement, when you change that and you measure how far you went and you measure how much time it took to do that, what are you measuring?
Movement? Vector. Dang, I remember you said something about this, but I forgot. Velocity.
Right?
Okay. Yeah.
Yeah. Okay. So you're measuring velocity when you're doing that. That's why I like to have it in this form. Also, I like when I read these tables, I typically read the top as my input, which gives me the output. Input, output. X's, Y's. X's typically we do delta Y output, change in output with respect to the change in input.
Okay. So wait. So okay. And also, I have a quick Rubik's cubing question.
Okay.
Ask me. I know how to solve it. Can you solve it, Mr. Rosenthal?
Yes, but right now we cannot. I apologize. We cannot do Rubik's stuff right now. There are lots of YouTube videos on it that are great. All right, fine. Make it quick.
Oh gosh.
Wait. So do you know about that like algorithm stuff? It's like uses all those different like letters like.
Yeah, but I don't memorize it by algorithm for the traditional cube. So I can't just tell you what the algorithm is over the video at the moment.
How do you usually do it?
I do a somewhat intuitive approach, and then there is some algorithm I throw in there, but I remember it through muscle memory, not by letters and numbers.
Yes.
Okay. Bye, Mr. Rosenthal.
All right, bye, Everett.
Thank you for helping.
You bet. Any other questions?
Thank you, Mr. Rosenthal. Thank
Okay.
you.
Bye, Jasper.
Bye.
Bye, guys. Have a great day. Enjoy your day.
You too.
Ethan, Shaya, Siwoo, anybody have questions? Tom, do you have any questions?
Yes, fabulous class. Classes.
This is my bedroom, by the way.
When did you grow the beard and when did you grow your hair out?
Oh, I've been in the winter I did the beard and I've been trimming it, and then the hair growing out is just, I think I like it. So I did that before the quarantine. Thank you,
Mr. Rosenthal.
Thank you. Yeah. So
at first when I saw a picture, I was like, wait, is that Mr. Rosenthal with the beard?
Yeah. Oh man, it's bad. You can see it in the back here.
Yeah, in the back, the hair looks good.
Yeah, it's good when it sticks out the hat. Although I might have to move to the south.
It looks good. You look like a NASCAR racer.
Yeah, exactly. But it's a Boba Fett hat, though.
Oh, it is. Oh, I didn't even notice that. I
Yeah.
noticed yesterday you had your Star. I like your choice of t-shirts. Yesterday you had the Star Wars t-shirt.
Oh yeah. That's my Star Wars gear.
Yeah. It's cool stuff. Cool stuff. Hey, and a quick question for you. Or a couple questions. You mentioned yesterday that you're recording these. Is that right?
Yeah, they're all on YouTube.
Is it publicly accessible or what's the
Yes.
channel?
You just search my channel.
What's your channel?
Joshua Rosenthal.
Okay, all right.
Yeah, and you'll see my geometry videos, and you'll see these videos, the pre-algebra. Did you catch my morning geometry session?
No, I didn't know. What time is geometry session?
That's 8:30 to 9:30.
And so, how many? There are a lot of kids in this class.
Yeah, and this is all my classes together, which makes this kind of learning pretty efficient.
Okay, so this is the multiple classes together. Okay, got it.
Yeah, I have 2 pre-algebra classes and 4 geometry classes. So totaling there should have been 70 kids in here. But there are the type of kids in a class that typically don't ask questions. They kind of get it just by observing and those are the type of kids that choose to watch it later, I suspect.
Yeah. No, I like the pace at which you go. It's pretty much, hey, here it is, boom, 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 let's move forward, and kids seem to get it.
They do, and the only thing is I don't know which ones are not getting it because they're just laying in the background quiet.
Right.
But if they go later and go to the video and look it up again.
Right. Cool. Another question: by any chance, do you have like that PowerPoint or that simple presentation that shows sort of the mechanics of the school? Or I guess the main thing I'm looking for is what the electives and clubs might be.
Yeah. She didn't get me. Miss Huff was not able to get me the PowerPoint right away. Did you ask Nikki Fong for her highlight reel? That might.
I saw that, but I think it's the PowerPoint that is what I was looking for.
You want the PowerPoint, not the. Okay.
I think that is more of the nitty-gritty details, I guess.
I'm going to ask her again today. She said that it's so much has changed since that we were giving that PowerPoint in the fall that she felt bad about giving you something that wasn't accurate.
Got it. Oh, okay. Okay. So rough feel from 30,000 feet. What's the situation there? I guess with regards to electives and things like that. I think when we toured, there was actually like an art class.
There will be an art class next semester. Yes.
Okay. So there will be an art class.
There'll be journalism. There will be forensics.
Art, journalism, and 6th graders take one elective. Is that how it works?
They take one elective and they double up on their science. So they have double block science. One is science. The other is called robotics. And they all.
So robotics is okay. So robotics is a class.
It's not the same type of robotics you're thinking. We call it robotics, but it's really a double block science. And then,
okay.
Yeah, and they supplement with programming in there.
Okay.
Yeah. So it's not a traditional robotics class, but we do have robotics teams. Our VEX robotics team typically wins the national championship.
Right. That's a after school club, I guess. Right.
It's after school. Sometimes it's during school. Sometimes they're in another state competing during school time.
Right.
So they're and we have on the second floor of our school. We have a robotic, they took 3 classrooms, knocked down the walls, and made a robotics lab for VEX Robotics. And so we have I think we have 2 fields in there where they can practice in there.
Right. That's separate from the maker lab you have, is that right?
Yeah, the makerspace lab is done by the guy who teaches our 6th graders the programming. He does an after school class on programming.
An after-school class.
Yeah, he does an after-school class on programming for kids that want to learn extra programming. But all students learn a basic programming. I think they do Python.
Right. He was the
Bradfield.
dad, right? And he was a dad, and he worked as an engineer, and then he came on as like a full-time staff or something, full-time teacher or something like that.
Yeah,
Is that the gentleman I'm thinking of?
Yes, Chris Bradfield.
After school class, cool. I'm sorry. Do you need to run?
No, I do not.
Okay. All right. So you've got art. You've got journalism. You got forensics.
Let me just address the students that are still in here. Are there any students that have any more questions? If not, I would ask that you sign out. Ethan, Eileen, Siwoo.
Wait, I have a question. I asked it in the chat, but then you weren't replying.
Okay, go ahead. What is your question? Sorry, Tom, if you could just give me one.
Yeah, no, of course.
The retakes we took before leaving school, like what's gonna happen to them?
I'll be grading them. I'm almost ready to grade those. So just keep an eye out. You should probably see it during spring break show up in the grade.
Okay, thank you.
Okay. All right, Eileen. Any other questions, Ethan or Siwoo? No? Okay, I'm gonna remove you guys, nothing personal. They might have just left their computer on.
They might be in the back having in a different room.
Did you say campaign?
No, I said they might just be in a different room having a bowl of cereal or something.
Oh, I don't know why I thought you were saying they were in a like a Dungeons and Dragons campaign.
Oh.
Because that's happening on Zoom now. So.
Oh yeah, everything's happening on Zoom.
Yeah,
how are you?
Family. I went. My brother and his family and my mom. We just all did a Zoom last night for dinner.
Oh, I was trying to get my dad set up on Zoom, and it's a little bit difficult.
Yeah. I was going to try my dad today, and it's going to be that kind of challenge.
Yeah. And he just called me, and then I think someone sent some one of his high school buddies. They're a little more susceptible to online scams. So I said, oh, you got to check out this file. So I'm going to open it. So I think he downloaded some spyware onto his computer. And
oh no!
His comments was like, hey, this big screen just popped up. I'm like, oh my god.
Oh my god.
This is not the thing to diagnose remotely at this time. But anyway, okay. So you're elective. You said you got art, you got journalism, you got forensics.
And then we had speech and debate this year, but it's going to change because we have a 7-period day. Period 2, most of the 14, 15 teachers, more than 2/3 of them are going to have an elective of their choice.
Elective of their choice.
So
wait, hold on. Okay, hold on 1 second, Josh. Hold on 1 second, please. Sorry, my son jumped on a Minecraft thing with his friends.
Oh, no worries.
Yeah. Okay, so you're saying every teacher's going to have an elective?
Most of them, unless they have a conference that period.
Okay.
So there'll be all sorts of things that there'll be a lot of choices.
Uh-huh. And what are you doing? Are you doing the journalism again?
No. Okay, so the likelihood, this is news, and you can't share it with anybody because it's not set in stone, but it pretty much is. I'm probably going to be AP.
Really?
Probably.
Oh, you're not going to teach?
Come out of the classroom.
Okay.
Which was always going to be the goal. Was always going to be the goal.
Yeah. Congratulations.
Thank you. But I am going to be involved in instruction, especially in the math department. And, our other math teacher, he's going to be the physics and the calculus teacher.
Right.
He's excellent, Mr. Knaus.
Right. Is he going to be teaching all the math then, or what?
No. So we're going to be having to we were going to be picking up a new math teacher this year anyway. And then now we'll have to pick up a second one to replace me if that goes through.
Right. Very cool. Very, very cool.
Yes.
That's onwards and upwards.
It is onwards. I don't know if it's upwards. I have a feeling that I'm enjoying teaching so much.
Right.
I feel like I'm not going to be as happy.
Right.
It'll be definitely a give and take.
Yeah. The AP, you got to deal with a lot of district issues.
Yeah, and even now with the way that the district does things, I get it. It's a giant machine that has to check boxes.
Yeah.
But it doesn't. Most of that stuff doesn't apply to our school.
Yeah.
They want us to do all extensive PD on Edgenuity.
Yeah.
Really remedial stuff doesn't pertain to our student body.
Yep.
But we have to do it because there's no way for them to differentiate or waiver that out in such a short notice.
Yeah. We had that same issue here. The teachers were pretty much up in arms. It's like, hey, this is not something that's really applicable to us, and we're already doing this and that, and we want to get time with the student. I mean, I understand what this is saying, but again, I don't think it really applies to
And they
our
cancel
teachers.
my lessons. They wanted me to do the PD this morning.
Yeah.
I just blew it off.
Yeah. No, they're saying, hey, you got that this week. I think at Kessler, the teachers are required